Welcome to a new lesson, Factors and Multiples of Whole Numbers. Before we start the lesson, we need to define what a prime and a composite numbers are. A prime number has exactly two factors, 1 and itself. A composite number has more than two factors. A factor is a number that multiplies to get the number we're looking for. For example, 2 times 3 is 6. The factor of 6 is 2 and 3. Also, 6 is a multiple of 6 and 1. Therefore, because 6 have 6, 1, 2, and 3 as their factors, 6 is referred to as a composite number. However, 1 times 2 is 2. There's no other factors of 2. That's why 2 is considered a prime number. So we're going to sort numbers from 1, 2, 3, 4, 5, and all the way to 30. So what are prime numbers? 2, 3, 5. I'm just going to do it all together for you. Here you go. 1 is neither a prime number or a composite number. 2 is a prime number, so it's 3, 5, 7, 11, 13, 17, 19, 23, and 29. And composite numbers are all even, all except 2, 2, 4, 8, 10, so on. Also, we have 9, we have 15, and we have 21 because 9 is 3 times 3, 15 is 3 times 5. They have more than two factors that are different. So make sure you understand the difference between prime numbers and composite numbers. Our focus will be on prime numbers in this lesson. So the first thing we'll do in this example is to write the prime factorization of 3,300. We're going to solve this with what's called a factor tree. We'll start with 3,300 and we'll ask ourselves, what are numbers that we know of that are factors of 3,300? Well, like the name of this number, we know there are 33 hundreds in this. There are factors of 33 hundreds. We're going to continue on and find the factors of the next line. Well, 33 is 3 times 11. 10 times 10 is 100. And we already found 3 and 11. These are prime numbers. We cannot further factor them along. So we're just going to recopy. But 10 is 2 times 5. And so is this 10 as well. So in other words, 3,300 is, we're going to do it in ascending order. In ascending order, so it's 2 times 2. We check off the 2's, times 3, times 5, times 5, and times 11. Also, our final answer should be written in exponential form. There are two 2's, so it's 2 to the power of 2, times 3, times 5 to the power of 2, times 11. And this is our answer when we prime factorize 3,300. Let's take a look at a different example. In our second example, we're going to determine the greatest common factor of 138 and 198. Now, the greatest common factor are numbers that both of these have in common. So what we're going to do is we're going to develop 138 and 198 separately in our factor tree, and we're going to factorize it, prime factorize it like we've done before. It is often a good idea when you're prime factorizing to start with very small common numbers, such as a 2. So let's start with a 2. 2 times what is 138? Then you would punch this in your calculator, 138 divided by 2, and you'll get 69. Then 2 is already a prime number, so we can't find factors of it. But we know that 69 is not a prime number. It's not a multiple of 2, so we can't divide by 2, but I bet we could divide by 3. So in your calculator, 69 divided by 3 will get you 23. And 23 is already a prime number, so it's 3, so we are done for 138. So this is prime factorization of it. We could do the same process for 198. 198 is an even number, so we could divide it by 2. So 2 times 99, 198 divided by 2 is 99. 2 is already a prime number, so there's no change in it. But we could divide 99 by 3, and we'll get 33. We can continue on finding the prime numbers of 33, but not of 3 or 2. 2 and 3 are already prime numbers. We could divide 33 by 3 and we'll get 11. And now we are done, because all of these 4 numbers are prime numbers. So right now we just prime factorize 138 and 198, but we did not find the greatest common factor. The greatest common factor are the factors that are in common with 138 and 198. Well, what are those numbers? What are those prime numbers that are in common? The 2 is common, so is the 3. This means that the greatest common factor, or shortcut, greatest common factor is GCF, is 2 times 3, which is 6. That is the greatest common factor for 138 and 198. So that 6 is the value. Let's take a look at a different example. Determine the least common multiple of 18, 20, and 30. Let's first talk about what a lowest common multiple is. The textbook definition of a least common multiple is of 2 or more numbers. That is the least number that is divisible by each number. That's a little bit difficult definition to swallow. I want to show you a little example first. For example, LCM, or lowest common multiple, of 2 and 6. We know that 2 times 3 is equal to 6. That means we have 3 multiples of 2 to get 6. But in order to get 6, 6 only needs to be multiplied by 1 to get 6. So the least common multiple of 2 and 6, it's actually 6 itself. We're going to use this example to help us solve the least common multiple of 18, 20, and 30. In order to do so, we are going to prime factorize 18, 20, and 30 separately. So 18, 20, and 30 separately. So 18 is 6 times 3, which is 2 times 3 times 3. For 20, it's 4 times 5, which is 2 times 2 times 5. And for 30, it's 5 times 6, which is 5 times 2 times 3. Let's list them now, one above the other. So 18 is 2 times 3 times 3, which is 2 times 3 to the power of 2. 20 is 2 times 2 times 2 times 5, which is 2 to the power of 2 times 5. 30 is 2 times 3 times 5, which is 2 times 3 times 5. What we are going to do is we are going to take the number that has the highest power and change it into red, such as the 3 to the power of 2, 2 to the power of 2, and 5 to the power of 2. And we're going to combine those values together, because the lowest common multiple is those numbers combined, or those numbers combined, which is 180. So again, we're combining the greatest power from each of these numbers and multiplying them to get the lowest common multiples. You could solve this question also in a little bit different way. You raise the powers, and let's focus on just the prime factors. The greatest common factor, GCF, is 2 because it's common to both. Actually to all of the 18, the 20, and the 30. And the LCM will be the greatest common factor 2 multiplied by some other values. So take a look at the numbers that remained. We have 3, 3, 2, 5, and 3, 5. Now we have to look at the numbers that are repeating. So we have a 3 repeating and a 3 repeating. So we're going to write one of these 3's. We also have one 5 repeating and another 5 repeating. So for both these 5's, write another 5. We also have a 2 and a 3 left. So we're going to finish off the 2 and the 3. Multiply 2 and the 3. And we're going to get the same 180 as we got before. That's a different method to find LCM, rather than finding the greatest powers of all these 3 numbers and multiplying them together. Let's take a look where lowest common multiples and greatest common factor are used. What is the side length of the smallest square that could be tiled with rectangles that measure 16 centimeters by 14 centimeters? Assume the rectangle cannot be cut. Sketch the square and rectangle. So let us draw the picture for the square. So here's a square where the 4 sides are equal. And let's draw this rectangle of 16 by 40. So what the question is really asking is how many of these multiples of 16 can go across, and how many of these multiples of 40 come across to get the same value. In other words, what the question is asking is what is the lowest common multiple of 16 and 40. So again, we're going to prime factorize 16 and 40. So 16 is 4 times 4, which is 2 times 2 times 2 times 2. 40 is 4 times 10, which is 2 times 2 times 2 times 5. So let's make a list again of 16, which is 2 times 2 times 2 times 2, which is 2 to the power 4. And 40, which is 2 times 2 times 2 times 5 is equivalent to 2 to the power 3 times 5. Let's find now as the highest power. Well, in this case, we have only one power, which is 2. And for the 40, we have the highest power is 5. So our lowest common multiple is going to be 2 to the power 4 times 5, which equals 80. This means it will be 80 centimeters. That means from one side to the other, it's going to be 80 centimeters. And the other side of the square is going to be 80 centimeters as well. This means we could fit 2 tiles across, down, and we could fit file 5 across, because 5/16 go into 80. So lowest common multiple can help us to, in this case, tile a square. Now we're going to focus on part B. What is the side length of the largest square that could be used to tile a rectangle that measures the same dimensions, 16 centimeters by 40 centimeters? Assume that the square cannot be cut. Sketch the rectangle and a square. So let's make this sketch. So we have 16 centimeter by 40 centimeter rectangle, and we want to fit it in a bunch of squares. But we don't know how many squares we're looking for. In other words, what the question is asking is, what is the GCF, the greatest common factor, the common factor for 16 and 40 to fit these squares? So again, we're doing factor tree for 16 and for 40. To find out, it's 4 times 4, 2 times 2 times 2 times 2, and 40 is 4 times 10, which is 2 times 2 times 2 times 5. And we're looking for the common numbers that exist for both 16 and 40 for their factors. And those common values are the 3 2's. 2 times 2 times 2 is equal to 8 centimeters. This means that each square can be 8 centimeters. Their dimension is 8 centimeters. This means that we can fit 2 rectangles, because 16 divided by 8 is 2 squares along, across, and we could fit 5 downwards. 1, 2, 3, 4, 5. That means we could actually have 10 squares fitted in 16 centimeters by 40 centimeters that have 8 by 8 centimeters dimensions.